and properties and other things about multivariable functions only. Okay, so in your math one, you would have covered most of the topics we are going to see for multivariable functions for single variable function. Okay, so now we will see everything for multivariable functions. Okay, so before that, quickly, if you have a function f from any domain D, so here D is a subset of R, right? So here D is a subset of R. Suppose you are having a function f from D to R, where D is a domain in R. Okay, so you may have some function like this. So here, for example, this is your domain, and all the points where f of x lie, that is your range, right? So this is the basic thing about a function, right? For example, suppose you are having f from R to R. So f of x is equal to x square, f of x is equal to 2x. So this kind of functions, you see that it can have the entire entire R, it is defined. Now suppose, for example, if you want to define f, or let's say g, suppose you want to define a function like this. Now you have to choose your domain carefully, right? So now your domain is like this, right? So this is what is the basic thing we see about function. What is the domain? What is the range? What is a graph, right? Okay. So for such functions, what you have already learned, how to find the maximum, minimum, right? Using derivatives and some derivative test and so many things. You would have learned how to find the maximum, minimum and all, right? So for example, suppose a function is representing temperature over a given time interval, or the altitude of a plane as it travels from point A to B. So such functions, you will find what is the maximum temperature, or what is the maximum height. So such things you would have seen, right? So now you see that the function is having only one variable, right? Now the same thing, this temperature can depend more than can depend on more than one variable. Maybe it can depend on location and time, right? Or you consider the profit model of a company, it may depend on the number of units sold, it may depend on the money spent, right? You can in fact add many other variables also, not just this, right? So in these cases, you see that here you have only one variable, so temperature over a given time interval. So this time is your only variable, right? And here altitude, right? Altitude over a given from a point A to B. So at a given time or a distance, what is altitude? So again, only one variable is there, right? But here you see we have two variables. So one is the location, the other one is the time, right? Same way you have number of units sold and the amount of money spent. So one thing depending on two or more variables. Okay, so in that case, we need to have multivariable functions, and to understand what is going on for these functions, we need some properties about these multivariable functions as well. Okay, so let us first properly define what are multivariable functions. Okay, so multivariable functions, depending on what is the codomain, okay, it can be splitted as scalar valued and vector valued. So what are scalar valued multivariable functions? A scalar valued multivariable function is a function f from D to R, where D is a domain in Rn. Okay, so in both these cases, your D is in Rn. Okay, so Rn means instead of just a scalar, you are having a vector now. Okay, and your n is greater than 1. Okay, and for scalar valued, your codomain is R. Okay, and for vector valued, you have the same f from D, where D is a subset of R, but now your codomain is Rm. In this case, you see n and m are both greater than 1. In this case, only you have n, and that n is greater than 1. Right? So for example, let us say you have f from R2 to R. Okay, so now f of x comma y, I can write x plus y or xy, right? Many things are possible. So now tell me, is it scalar valued or vector valued?
Scalar valued.
Yes, this is scalar valued. In short, I will write SV for scalar value. Okay, this is scalar value. Now suppose I have f from R2 to R2 itself. Now I'm writing f of x comma y as xy comma x plus y. Now this is vector
Vector
value,
valued.
right? So here are some more examples. So tell me, so for the following functions, first of all, tell me what is the domain, what is the codomain. So based on the codomain itself, you can tell whether it is scalar valued or vector value. So for the first one, what is the domain
R2.
R2.
and codomain?
R.
R. If it is R, then what is it? Scalar valued or vector
Scalar
value?
valued.
Scalar value.
Scalar valued, right? What about option two?
R3
R3.
scalar value.
So
R.
codomain is R and it is scalar valued. What is the domain for option three?
R3.
R3
3.
R3.
and R3.
R3.
Vector valued.
Vector valued. Fourth one,
R2. R2.
2R2.
it
Vector
is
valued.
vector valued. The last one,
R2 to R.
R2 to R scalar value.
Scalar valued.
okay. So what are scalar valued and vector valued is clear for everyone, I guess, right? Okay. What about linear transformations? So
Ma'am, a small in option two for logarithm functions, only positive side of
Codomain.
R should be taken
you're
as
okay. Maybe let us say you have a domain in R3. Is it fine now?
okay. Yes.
Okay. Okay. So now linear it's good that you noted it. Okay. So next, so let us look at some examples, some familiar
Ma'am,
examples.
someone is calling you.
Yes.
Ma'am, exactly what we need to check of scalars, if there is, like, we need a variable only check.
See, we are checking whether the function is having a range in scalar values or in vector values. Okay, so where it is mapped to. So for example, let us take this example here. You see, whatever values you take from R2, it is mapped to some scalar values. But here they are mapped to some vector values.
Ma'am, somebody just pointed out that domain is a subset of R3. I think it is not, ma'am. I think the domain is R3 only, because if we have -5, we can put y and z as 10 and let's say 15.
See, that's why
Then
I
it
did not
become,
want. See, that's why I did not want to go into this. See, as
it
long as
is
you know that it is a
technically,
domain in see, let's not go into
it
the
is.
technical part of this.
Okay, ma'am.
See,
Sorry.
one thing is that here you see that it is as long as D in R3, it can be R3 or any subset of R3. Okay, so what is going here? Maybe let's discuss it later. For now, let's first see what are scalar valued and vector valued. About logarithm especially, we will discuss later. Okay, so D can be R3 or subset of R3.
Yes,
Let's
ma'am.
see in detail
My
about it
mistake.
maybe
It
later.
should be x plus y plus z greater than 0. My mistake.
Okay.
Yeah.
Okay. Okay. Fine. Okay. So where were we? Yes, the other student who asked the doubt. I don't know exactly what you were asking, but is it fine?
Yes, ma'am.
X plus y plus z are greater than 0.
Okay, fine. Okay, so now for some examples here, linear transformations are very obvious examples, right? So for example, here R2 to R2, you can take R3 to R3 or R2 to R. So linear transformations can be both scalar valued as well as vector valued, right? So maybe we will take one scalar valued example and one vector valued example. Can you tell me one scalar valued example of a linear transformation?
Just
F
you
of
write it.
y is
Inner
equal
product.
to
Fxy equal to x square y square.
x square.
X squared plus y, x squared plus y square. Okay.
Ma'am, could you give how inner product is an example?
Okay. Okay. So in that case, okay. If you want to define with an inner product, so f of x comma y, maybe we have to write it as inner product x comma y. That will maybe work because inner product x comma y is a scalar. But here, but no, it does not make sense. X and Y both together is a vector, right? So if you want to use inner product, then maybe we have to do something else. It's not very straightforward how to use inner product here, right? No, we cannot just like that use inner product here. Okay.
Ma'am, if we are defining my function in that way, then it's possible. No?
Yes, ma'am. If
In
a
which way?
function is defined as an inner product,
No.
no, in the
See, for
professor's
inner product, you need two vectors.
yes,
Correct? What is the other vector? One vector is x comma y. What is the other vector?
No, okay. Norm of the vector itself, like the length of the vector can be.
See, using norm, that is a different thing.
Yes,
Okay?
yes, correct.
But inner product means you need two vectors. Norm, one vector is sufficient, right? But if you are taking it as a norm, you
Then
have
it
to
would
check
be
so many things.
technically it would be a composite of a multivariable function. If I'm
See,
correct.
here first of all, x square plus y square you are saying, but will it be a linear transformation?
No.
No, right?
No,
Why did you say
no.
x square plus y square?
This is the scalar value.
3x plus y, maybe
Yeah?
3x plus y or something like that.
Yeah, x plus y will work. Okay. Now, what about f from, see, for this course, like for multivariable functions, you don't need linearity at all. But since this particular example is about linearity, we are looking for it. Okay. So next is f from R2 to R2, f of x comma y, maybe simply x plus y, x minus y. Okay, fine. And examples of polynomial functions, this also now can take scalar valued and vector valued. For example, here let us take x comma y as some x square y. Okay, and f from R2 to R2, then here f of x comma y.
Ma'am?
Yes?
I'm showing the above one example you are taking from scalar valued and one you are taking from a vector valued, right?
Yes.
Okay.
This is vector value. So here, maybe we can take simply x cube or x plus y square or something like this. Okay, it's polynomial functions. And then arithmetic combinations like sum or multiplication. Multiplication in the sense here mainly we are looking at composition. Multiplication in general is not making sense for vector valued. Only for scalar valued it will make sense. So we can take addition, subtraction, or composition of functions. So composition in general, you know what are composition of functions. So the same kind of definition holds for multivariable function as well. Okay, exactly the same definition in fact. Okay, so let D be a subset of Rn and f be a function from D to Rm. Okay, now let us consider another function g which is from E to Rp. So to define G composition F, what is the condition we need? To define G composition F, we want the range of F to be contained in E, right? This is the usual way we define composition, right? So only when the range is contained in E, you can apply G to this E, right? So because you have G composition as F means G of F of X. So this F of X should be inside E, then only we can define G composition F. Okay, so G composition f of x is G of f of x for all x and b. So note that here x has this tilde in the bottom to specify that it is a vector.
Ma'am, one small doubt. Is
Yes.
R2 a subset of R3? Is that a correct statement?
No, incorrect. No.
Incorrect. Okay.
Okay. Please never ever say this. I have rejected during the TA selection. I have rejected many students because of this particular statement. Okay, never use that.
Yes, ma'am.
Ma'am, please repeat which statement.
R2 is a subset of R3. We cannot say that. No. R2 is a different space. R3 is a different space.
Ma'am, I got confused because R2 is considered as the XY plane in R3. No, so that's why.
See, that is they are isomorphic. So that is why unit 7 is important. What is the see, the structure is preserved in XY plane. But R2 means you are having only two coordinates.
Right, correct, ma'am. Got it.
Okay. Fine. Okay. Okay, so here you have a question. If two functions f from R2 to R and g from R to R are defined as f of x comma y is equal to x minus y and g of x is equal to sin x, then which of the following function represents g composition f? A very simple question only. So you have g composition f. So f is from R2 to R. So you have here x comma y. So you have g of f of x comma y, right? Okay, so now you see that f of x comma y is defined as x minus y. So g of x minus y. So now tell me, what is g of x minus y?
Sin x minus y.
Yes. Okay, so which option is the correct one?
Option 2.
Okay, fine. So very simple exercise only. So a similar exercise is here. So let us say you have two functions f and g. So f is from R2 to R and g is from R to R2. So here you have f of x comma y is xy and g of t is e power t e minus t. Which of the following function represents g composition f? So before answering this question, let me see how many of you, I guess everyone knows this, but anyway, just to make sure. So let me define another function h in this way. So your h of x is e power x comma e power minus x. So what can you say about h and g? What do you note? What is
Both
the
are same.
both are
Same.
same, right?
Yes,
So
ma'am. Same.
yeah,
Both are same.
only we are changing the notation for the variable.
There is something wrong with the superscript, ma'am, of e to the power minus t.
Yes, yes.
Something.
The graph looks same for both.
It is the function itself is same. It's not just the graph. The function itself same. Okay, both g and f h are same. There is no difference in them. Okay, so only the variables are different. Okay, so whenever you see some t, you should not think that something different is defined. Okay, x or t or whatever, it should not
Lots of
confuse.
variable.
Okay, they are just denoting some variables. Okay, fine. So
Ma'am,
question, yes.
if two function produces same graph, then should we call them also same?
Yes, if for the entire domain you get the entire range is the same values, yes, they are same.
Maybe let's say they have like one is expanded, another is somewhat manipulated in equations or something.
See, usually they are same, but sometimes if you really want to make them different, then you like, let us say you have a function f of x is equal to mod x. Okay, and you want to write the function something different, then you write g of x is equal to x for x greater than 0, 0 for x is equal to 0, and then minus x for x less than 0. I don't know whether you call them different or same function. It depends on how you define what is equal. Actually they are same only, right?
Yes, ma'am.
Okay, so usually this
Yes.
can be the difference. There cannot be more than this kind of difference if the graphs are exactly same. Okay, fine.
Yes.
The way of definition maybe are differing, but technically they must be the same. Okay, fine. Okay, so continuing here, g composition f of x comma y is g of f of x comma y, right? Now what is f of x comma y?
XY.
Xy. So now if you apply g to xy, what will you get?
E to the power of xy, comma, e to the power minus xy.
Right? Okay. So now which option is coinciding? Option
Option
3, I think.
3. Okay. So option
Ma'am,
3
g
is,
of fxy is g of xy.
sorry, what? Yes, g of f of
Uh,
x comma y is g of xy. Yes. What's your question? Is it clear?
Got it, ma'am.
Okay. All right. So here you have some arithmetic operations on multivariable functions. So sum, you can add two functions by splitting them. You can do the scalar multiplication and split them. And only when m is equal to 1. Remember, these two are defined only for scalar valued functions. Okay, so when m is equal to 1, only then you can define product function and quotient function. Right? Otherwise, what is the product of two vectors and the division of two vectors is not defined. Right? So this is defined only for scalar valued functions. And note that for the quotient, you need the denominator to be non-zero for all the entries of your domain. Okay? Fine. So these are the basic things about arithmetic operations. So a very obvious exercise is here. Quickly read it and tell me which of the options are true. It is a very straightforward one. Just see this and answer this.
Except for one, everything
2
is
and
true.
4.
2 and
4.
Sorry, ma'am. 2 and 4, yes.
okay, so this one should be just C instead of 1 by C. And here it is valid only if
M equal
M
to 1.
equal to
Yeah.
1.
valid only if m is equal to 1. So this is incorrect. Yeah. Okay. So you know that, for example, if you have a function f from R to R, you have f of x is equal to maybe, for example, x square, then you know that the graph is represented on a plane. Right? Actually, it should touch. Yeah. So the graph is represented on a plane. Right?
And it should be R to R square, right? Oh, sorry.
Okay,
Sorry.
so many may have this kind of a doubt when you look at this graphs. That's why specifically have written what is this. See, f from R to R, f of x is equal to x squared. You see the graph is now an image in the plane. Okay, so same way, for example, if you take functions of two variables, then you see surfaces in R3. Okay, so functions of two variable, you can see surfaces in R3. Beyond functions of two variable, like functions of three variables or more, can you visualize? For
No, ma'am.
functions of, no, right? So till functions of two variables, you can visualize them. Right? Beyond that, we cannot visualize. Okay, fine.
Ma'am, once could you repeat from x square, f of x equal to x square once? I couldn't understand. What
Okay.
you
See,
wanted
for
to
a
say?
function from R to R itself, you need R2 to look at the graph. Right? Both the domain and codomain are R, but you need R2 to visualize the graph. So for a function, for example, for f from R2 to R, you will need R3 to visualize the graph of f. Right? In that case, you will call the functions graphs here to be surfaces. Right? So you see that beyond R2, if your domain is beyond R2, then you cannot visualize. Okay, so in general, we refer to their graphs as curves only. Okay, fine.
Yes, ma'am. Understood, ma'am.
Just a terminology, nothing more here. Okay. Okay, some more terminologies which we will be using frequently. What is open ball? Okay, open ball, center at A with radius R. First, let us see what is this in R. Okay, so let us consider the real line and let us take a point A. Okay, so let us take R radius. So you take a distance of R and you take a distance of R on either side. Okay, so now the word open is mentioned. So I'm putting this open bracket. So you have, what is this point now? This is A minus R and this is A plus R. So now this open interval A minus R, comma A plus R is called your open ball at A with radius R in R. This is in R, real line. Okay. Now let us look at the same in case of R2. So in case of R2, let us say that you are having some point x here. Okay, if you want to, maybe you can take it as a also. Let's say you have some point a and you are considering radius r. So you have a ball here and you are considering open ball. So open ball means what? Points on the boundary are not included. Just like an open interval, the boundary points are not included. So here a minus r and a plus r are not included, right? So same way, the points on the boundary of this ball, points on the boundary of the circle. Of the circle are not included.
Ma'am, this will look like a sphere in 3D, right, ma'am?
Exactly. In 3D, it will look like a sphere, but sphere where the outer shell, that is not
It's not
included.
included. Okay.
Okay.
Only the inner part of the shell.
Ma'am, is a sphere in three-dimensional space, is it considered like a surface?
Yes, you can say.
Ma'am, could you once go to that slide, previous slide, just the diagram? Yes, ma'am. So it's considered a surface, ma'am.
Yes.
Any
Yes.
okay.
Yes. So here you see that. So all the points inside this are points inside the open ball. Okay. So next thing is standard ordered basis of Rn, which everyone know. The notation is EI 1 less equal to I less equal to n. So
Yes,
what?
ma'am,
Yes?
what is the
Sorry?
the dimension of this sphere in this case?
See, this one we are seeing in R2. So the line we saw in R. So this is in R2. Okay.
So this open ball is the set of all points which are inside this sphere.
Exactly. Inside the circle here. Yes.
It depends upon the dimension of the space we are looking at, right, ma'am?
Exactly. So here norm of x minus a means you have already seen what is norm, right? So it means what? You take any point x. If the distance between x and a is less than r, then that point x belongs to this open ball. Okay?
Yes. Okay.
So standard ordered basis, you know that this is the notation where EI represents this kind of a vector where the ith coordinate is 1 and all the other entries are 0. Okay. So what is an open ball and standard basis? I hope everyone is clear with it. Yeah.
Ma'am, standard basis of Rn is
Yes.
what is the written here, like what it means to it.
What it means, we have covered this in the previous weeks itself. What it means what you are asking.
I'm asking like EI 1 less than equal to I less than equal to n means कि ये 1 और n के बीच में रहेंगे.
E1, E2, En. This set I am writing it in this way, that's all. All this E1, E2, En. Your I is varying from 1 to n, so you have all 1 to up to n, that's all. Okay.
These are related to the values 1 to the nth.
Yeah, your I is changing from 1 to n, that's all. This is just a set notation. Okay. So suppose y is a quantity that depends on another quantity x. So y is a function of x, right? So you will have a curve like this. So I don't know how many of you have gone through this, what is that called? Tutorial videos or, no. For before week 9, you have this bridging videos which is provided in your course page. I forgot the name of that particular section. How many of you have gone through it?
Ma'am, where
Revising
it is,
one variable calculus.
I don't know, ma'am.
Never seen it.
Yes, ma'am. I don't think we.
The tutorial videos are there. Please.
These are on the playlist, but not on the portal.
Yes, ma'am. For statistics, we had week 0. I don't think we had week 0 for.
No. Week 0 is not there, but it is somewhere maybe after
is
week
in-
6 or
Don't
week
recall.
8.
The dashboard is not there, ma'am.
No,
Yes, ma'am.
dashboard is not
It
there,
might be in
but
the
it's
YouTube.
it's
It
in
might
the
be in YouTube, but
playlist.
it's
Okay,
not
if
there.
not, just go through the YouTube videos, maybe just to have a quick recall of your week 1 topic, so that you will have a continuity when you go through the topics of week 2. Okay, so please go through
Ma'am,
that.
someone was trying to help us out. I would like to ask that person to just share that link in the chat box, please.
Playlist that. Yeah, sure. Just a second. I
Okay,
Ma'am, why not continue?
sorry.
Ma'am, let's continue now.
Yes, let's continue. Okay, so now consider the graph of f. So you have the graph of f. How do we usually define the rate of change? So for considering the rate of change, what is that we do? This is your actual point P, right? So you have the point A comma f of a, right? So now to find the derivative of the slope at this point, right? So what do we see? We have to first of all look at what is the tangent line. The slope of the tangent line gives the derivative of the slope at that point. But how is that tangent obtained? So for that you take point like this on the curve, which is at a distance h, and then what is the rate of change? That is f of a plus h minus f of a divided by h. So distance in y, variation in y by variation in x. As h goes to 0, slowly you come to this point. So this is how we are defining the slope of the tangent at a point, right?
Yes, ma'am.
So this is for one variable. Just a quick recall I'm doing. I'm not explaining here. I'm just doing a quick recall. So keep this in mind. The exact same thing is what we are going to see for multivariable functions also. As I told you already, we will not be able to visualize for functions beyond R2. Okay, so that's why here I am particularly considering functions of R2 to explain it. I guess, okay, it comes after this question. So first, just look at the definition, and then we will look at the explanation part. So for a function f of x1, x2, xn, okay, with domain in Rn, containing a point A tilde and an open ball around it. Okay, so we need definitely an open ball around it to define this rate of change. Okay, so here A tilde is inside an open ball, some open ball. Okay, the R can be anything. Okay, but A should be inside an open ball, and that open ball is inside your domain. Okay, then the rate of change of f at A with respect to the variable xi. So for functions of one variable, so for f of x means your rate of change is with respect to x. Now we are having x1, x2, xn. So your rate of change of f is with respect to one of these variables. So I'm writing it as xi. Okay, so how is it defined? So it is defined as limit h goes to 0. So just exactly similar to this. So in the one dimensional case, you add limit h goes to 0, f of a plus h minus f of a by h. Now here, so what is that happening? The change is happening only in the direction of the ith coordinate. So I am making the change only in the ith coordinate of a. Okay, so HEI. So it means what? You are having 0, 0, H, 0, 0, 0. Okay, HEI. I'm adding this vector to A and then finding the limit. So this is the rate of change of f at A with respect to the variable xi. So now if I'm just applying the definition, how will I find the rate of change of this function? Okay, you have to exactly apply this definition. That's all. So let's see how to do this. So here, you are given this function, you are given this point. So this is your A tilde. 1, 2, minus 1 is your A tilde. With respect to z. So z means the third coordinate. So if it is the third coordinate, here your EI is what? Your I is
0, 0, 1.
0, 0, 1. So it means you are taking E3, which is 0, 0, 1. So it means what? You are considering limit h goes to 0, A plus H3, HE3 minus f of, so here also f is missing, f of a by h. So now this is your a, and plus HE3, what is the value? 1, 2, minus 1 plus 0, 0, h. What is that?
120.
1 to minus 1 plus h, right? So f of 1 to minus 1 plus h. And then here minus f of 1 comma 2 comma minus 1 whole divided by h. So now first tell me what is f of 1 comma 2 comma minus 1?
5x square minus 6x. Okay, we'll have to put the value. Sorry.
Yeah, substitute the values and calculate and tell me the answer alone. What is f of 1 comma 2 comma minus 1? F of 1 comma 2 comma minus 1. So 5 times of 1 minus 6 times of 2 plus 3 times of 1 minus
Minus 4.
2 times of minus 2. So 5 minus 12 plus 3 plus 4.
Minus 8.
So 8 plus 4, 12. 12 minus 12 is 0. Is it correct?
Yes.
Okay.
Yes, ma'am.
Okay. So now we have to do the same for the first part as well. So in your first part, note that this is your x, this is your y, and this is your z. Okay. Now substitute everything here. What will you get? You will get 5 minus 12 plus 3 minus 1 plus h the whole square minus 2. Your y is 2. So let's multiply it. Becomes 4 times minus 1 plus h. Minus 0 here divided by h. I forgot the limit. So limit h goes to 0. Here also limit h goes to 0. So in the numerator, so you have minus 7 plus 3 times of 1 minus 2h plus h square plus 4 minus 4h by h. Limit h goes to 0. So what is the numerator? When you simplify all the constants together, 0, right? The constant term is becoming 0. What about the other part? So you have minus 6h plus h squared minus 4h by h, which is actually, so minus 10h plus h squared by h, which reduces to just, did I make any error? So here it is 3h squared, right? So you have minus 10 plus 3h. Is that correct?
Minus 10.
Ma'am, we are taking this E3 because we have to calculate with respect to Z, right?
Exactly.
Okay.
So you have minus 10 plus 3h. So what is the limit?
Minus 10.
Minus 10.
Ma'am, in this case, our result is in vector space R. So we know how to calculate normal limits. But what if the vector is in some R2, R3? How will we calculate a limit of something in R2 and R3?
Okay. So usually whatever we are studying, like rate of change and other things, we are studying in this course particularly for scalar valued functions. But we have a topic which is called the limit of vector valued okay, here limits are also for scalar valued. So mainly everything is about scalar valued functions. There is only one topic where we see like, I guess it is sequence in multivariable functions. There you apply limit of multivariable sequence in multivariable functions, I guess.
So, ma'am, just to confirm,
Hmm.
if something converges, then the limit exists. If something diverges, limit does not exist.
Exactly.
That's it.
Ma'am, in this one, since we are like, we'll always, if this kind of a question comes, so we'll always take the standard basis. Like in this case, we have taken
Exactly.
E3
Yes,
Okay.
yes. See, we are in the very beginning stage. So we are trying to look at the definition, and from definition, we are looking at everything. But just like in, see here, this is the definition of finding the slope of this curve at this point. Okay. But suppose you are having some polynomial. Okay. Suppose you are having some polynomial. How do you find the derivative? Do you apply this formula?
Yes.
Or I should say maybe x squared plus 2x or something like. Will you apply this formula to find the derivative with respect to x? How will you find?
Yes, ma'am. This formula.
Differentiate.
Is
Differentiate.
you can easily
Why?
do 2x plus 2, right?
Yes, yes, yes.
So the
Differentiate.
same thing, see, this is the definition. So in the beginning, we try to understand it using limit, but
Right.
later on, once you get used to the limit and you know the formulas, you will simply just switch to the formulas. Okay, you will not be using the limit every time. Okay, but there are places where limit is necessarily used. Okay, we will see everything. Okay,
Okay.
fine.
Ma'am, someone has asked about convergent or divergent. I couldn't hear that. Could you just repeat that statement?
So someone just asked me if it is converging, then the limit exists, and divergent means limit does not exist. That's all he asked. I don't know who was it. Only
Okay,
this
okay,
much was
okay,
asked.
okay.
Yes, ma'am. That's all I asked. Ma'am.
Yeah. Okay. So now, so maybe I have this other page which I wanted to show. Hold on. This is the page, I guess. So is this GeoGebra page visible to you?
Yes, ma'am.
Okay. Fine. So you see that we are having a GeoGebra graph here. So I have taken y is equal to 1 and the function x square plus y square I have taken. Okay, so now you see you have this kind of a shape that is your x square plus y square. And this y is equal to 1 is your plane. You see, this y is equal to 1 is your plane. Okay, now where is this y is equal to 1 cutting this plane? That let us see how it looks like. See, this
Parabola.
violet part, the boundary of the violet part, this is your intersecting
Parabola.
part. Okay,
Yes.
okay, just this line, the boundary here, that line is your intersecting part. You see, just that line, this line you see. Okay, the same thing if you take for x also, you can see the similar thing. So if you are taking some fixed x value, then you see again just a curve. So here in this case, it is this curve. So this curve, you see, that is your intersection, right? So if instead of just one fixed x or one fixed y, if you are taking any other line like y is equal to x, then also a similar thing happens. So now in this case, this particular curve, you see this boundary, so that is your intersecting point. Okay, so you can see what is happening here, right? So with this understanding, so let us continue what we were saying. Hold on. Yeah. So how are we going to define partial derivative? We are going to use the already existing definition only. We are not going to do anything new. So what do we already know? We know if you have a function of one variable, you know how to define the derivative. So you are going to consider a function of one variable instead of considering the entire function. But how to consider just
Ma'am,
the
could you
function?
repeat that? Could you please repeat that, ma'am?
Okay, fine. See, now we are having a function of two variable and you are trying to look at what is derivative. So instead of defining something new, we are going to use what is already there. What is already there? Derivative for functions of one variable. Okay. So from function of two variable, how are we going to get a function of one variable? That is the only main part. So once you have a function of one variable, you already know what is the definition for the derivative of function of one variable. So for example, now partial derivative means usually since whenever we are having more than one variable, so here in this case we are having only two variable. So either you can talk about with respect to x or with respect to y. Okay, so if it is with respect to y, what is fixed and what is varying? If it is with respect to x, what is fixed?
Y is fixed.
Why?
Yeah, so your y is fixed and your x is varying, right? So here, what is it you are seeing? So I will try to approximately draw. I'm not very good at this 3D drawing and all.
So, ma'am, that plane that you just showed in GeoGebra, over here is x is equal to 0, if I'm not mistaken. Is that correct?
No. See, x is 0 is this line. We are somewhere away from that.
No,
Okay.
x is equal to 0 is a plane, no, ma'am, in here.
Yes, yes. So this blue line is your plane. But that here it is not x is equal to 0. It is away from this line. You see there
Oh,
is a gap
yes,
there.
yes.
Okay. So here this point is your x naught comma y naught. Maybe I use a different color. So this point is your x naught comma y naught. Okay. So this is your x naught. Approximately I am trying to do. And this plane, whatever is here, that plane is nothing but the plane of y is equal to y
Why
naught.
not?
Okay, y is equal to y naught, this blue plane. Okay, so your y is fixed. It is the fixed value. The value is y naught. Okay, now only your x is changing. Okay, your y is fixed. Okay, so in this case, so the intersection is, you see this blue line, and now this blue line, you see it is just a function of x because your y naught is fixed. You understand? So the function of two variable, when we are considering one variable as fixed and the other one as varying, we will reduce the function to a function of one variable like this. Now, since it is a function of one variable, we know the derivative. Is it fine? Do you understand what's going on? Yeah?
Yes.
Okay. So here, what is that happening? So we want to find.
Actually, in this case, one is fixed and other is variable. You have drawn the curve here.
Yes, yes. The intersecting, this curve is the intersection of this fixed plane and this entire surface. Okay, fine. So we are trying to find dou f by dou x, the partial derivative of x with f with respect to x, at which point? At the point x naught comma y naught. Okay. Now this partial derivative is simply reduced to just derivative with respect to x of this function at the point x is equal to x naught. Okay, are you able to relate whatever I explained here? Yes. Okay, good. So let us see it with an example. Consider the function f of x comma y, which is 2x squared y cube. Okay, let us determine the rate at which the function is changing at a point x naught y naught if we hold y fixed and allow x to vary. Okay, so it means what? Here you have f of x comma y naught, right? So it means what? You have 2x square y naught cube. So let us in fact specifically write what is x naught y naught, so it is even more easier to visualize. For example, if I am taking 1 comma 2, then what is your f of x naught comma y naught, or x comma y naught? It is simply
2x naught square y naught cube. Sorry, ma'am. 2x square y naught cube.
so 2x squared y naught cube.
2
But
into
what
y
is your y
squared,
naught?
8
Your y naught is 2.
16.
16x square.
16.
2 to the 4, 4 to the 8, and then again 2. So you have
Yes,
16.
sorry.
16x square, right? So now you are going to, so dou by dou x. Maybe I should write one more step here which is missing. So dou by dou x of f at x naught y naught is same as d by df by dx at x is equal to x naught. Okay, so at x is equal to x naught. So now what is the derivative of this with respect to x?
2x. 32.
16 times of 2x, right?
Yes.
32x.
Yeah, 32x at x is equal to 1 because x naught is 1 here, right? So 32x, which is exactly 32. Okay, do you understand? The same definition, I have just applied it for the specific function and the specific point. Is it clear? Yes?
Yes.
Okay. Ma'am, where you wrote df by dx and you put a line and wrote x is equal to x naught, won't it be y is equal to y naught?
See, y is equal to y naught is applied. See, at the point x is equal to x naught. Instead of y, I already applied y naught in this scenario.
Oh, okay. Yes, ma'am. Yes, ma'am. Sorry.
Okay, fine. Okay.
Yes,
So
ma'am.
now let us look at the same scenario when y is varying and x is fixed. Okay. So now you see your y is varying and your x is fixed. Okay. So here you see this is your point. So this is your point x naught, y naught. Okay. So now you see that you have, this is your plane. So your plane x is equal to x naught, and you have the y values varying. Okay, your x value is fixed, only your y values are varying. And you have a similar one-dimensional curve, right? So here the exact same definition which I wrote with respect to x. So here you see that x is fixed and y is varying. So you have dou f by dou x at x naught comma y naught. Sorry, here dou f by dou y.
Ma'am, just to confirm, here the z-axis is representing the value of the function, right?
Exactly, exactly. So here df by dy, maybe I'll write d by dy of f of x naught comma y at the point y is equal to y naught. Okay. So whatever function we considered earlier, so exact same function is here also. Now we are going to find the derivative with respect to y. So let us consider the same point x naught, y naught. Okay. Now what is dou f by dou y at the point x naught comma y naught? So it is simply d by dy of, now you substitute x naught here. So f of x naught y, x naught comma y at the point y is equal to y naught. What is f of x naught comma y? X naught is equal to 1. So it means what is the function you will get? D by dy of 2y cube.
Y cube.
2y cube at the point y is equal to 2. Right? So what is the derivative of this function?
6y square.
6y square at y is equal to 2. So it means 6 times of
84 answer.
Okay, clear? Yes?
Yes, yes.
Okay. So in general, now you see that the same definition, whatever we saw, it can be applied for any function of Rn. So limit h goes to 0, x plus hei minus f of x by h. Okay, so this is the usual limit definition which we saw. Okay, so just like we did for functions of 2 variables, so if you have a function of n variable and you are calculating the partial derivative with respect to only one variable, then you should consider f only as a function of xi while treating the other variables as constants. So here, if we are differentiating with respect to y, we considered f as a function of y and kept the other variable x as constant. Suppose you have more than 2 variables, x1, x2, xn. So for example, with respect to x1, if you are calculating the derivative, all the other variables, x2, x3, everything, you have to keep it as constant. Okay, and do the derivative calculation just like we did above. Okay, fine. Now here is, yes.
How would you, so partial differentiation with just normal functions like y is equal to x square will just be normal differentiation, no ma'am? Am I correct?
See, with respect to which variable you are doing, you are just, yeah, you are keeping one variable fixed and the other variable as constant. So if you are doing one variable as constant and you are not specifying any point, for example, you are taking x squared minus y, then suppose if you are differentiating with respect to x, y is constant, so that part becomes 0.
Right.
Okay. Yeah, we will see several examples like that. Hold on. Okay, fine. So look at this function. First of all, is this a scalar valued or a vector valued function?
Scalar, ma'am.
Scalar valued. So everyone quickly find what is the rate of change of f at 0, 1, 1 with respect to x. So instead of going through the limit definition, can we now quickly use the usual derivative formula which we already know? So what is dou f by dou x? So you know that y and z are constants. So if y and z are constants, when you differentiate this with respect to x, what is that you will get for the first term? xy,
Y.
Answer is
y,
one or
Y, only Y.
0,
and yz becomes
0,
0. And zx,
Z,
z, and here this one,
minus 3YZ.
3Y, minus 3Y. YZ.
Minus 1, ma'am,
okay.
for
So at the
option
point
B.
0, 1, 1 we should find. So let's see. Dou f by dou x at the point 0, 1, 1. So the answer is 1 plus 1 minus 3. So the answer is minus 1. So this is incorrect. So you calculate this and tell me the rate of change of the function f at 2, 2, 2 with respect to x is same as the rate of change of the function f at 2, 2, 2 with respect to z. So everyone quickly calculate what is dou f by dou x at
Yes,
2,
ma'am, that's
2,
right, I
2.
guess.
Ma'am, the second option I did not understand, ma'am. Could you please?
Okay, the second option we are okay, I put dou f by dou f, sorry, by dou x. So we are simply calculating the partial derivative of this function with respect to x. So with respect
Right,
to x
ma'am.
means y and z are constants. So
Right, ma'am.
now this y is just a number.
Right, ma'am.
Okay, so this number, suppose imagine it is 5 means when you find the derivative of 5x, it is simply 5, right? So that is what we have done here. Okay.
Ma'am,
Ma'am,
so with
Yes.
respect to x, that means we'll put the other two as constants.
Yes.
Ma'am, but this equation, what you wrote, dou f by dou x, uh, you're taking x as the constant.
No. See, imagine the same. Okay, let's say you have 5x, you have plus 10, and then here plus 2x minus 30x. So I have taken y to be 5 and z to be 2. Then what will you get in the derivative with respect to x? You will get 5 plus 0 plus 2 minus 3 minus here yz value is actually 10, right?
Right,
So 30. So minus 30 you will get. So the same is
right.
what I have written here. Now do you understand?
ma'am, so in
Yes.
this one, ma'am, like you're differentiating with respect to x, right, ma'am?
Yes.
So in this one, so we have kept the other two values other than 2x as constant, right?
Yes.
So, ma'am, how will you write this in like d by dx form? So we're doing d by dy of y and d by d of z of z. Are we doing something like
No,
that?
no. See, okay. I guess this is your confusion. So dou f by dou x, you are not given any specific point here. So let us say at some point x naught, y naught, z naught.
Right, ma'am.
Okay. So this is d by dx of f of, or yeah, x comma y naught z
Z
naught. Okay, so
Right.
instead of y and z, I am putting y naught z naught. That's all. Clear?
Clear, ma'am. Okay,
Okay.
ma'am.
Okay.
Y naught, Z naught.
So it means here you are having y naught z naught in place of y and z. That's all.
Ma'am, just a second, ma'am.
Ma'am, the equation I'm not able to understand is the first one that you wrote, ma'am.
This one.
Yes, ma'am. It's a bit confusing.
See, if you put y naught, that's why I wrote it in with numbers actually. See, if your y and z are given as 5 and 2,
Right,
then this is the equation you will have. Correct?
right.
So then what is the derivative of this with respect to x? 5 plus 0 plus 2 minus 30. Is that correct?
Correct, ma'am.
Ma'am, I
So
have
now
one.
what is your 5? 5 is your y. And in place of 0, you are having 0. In place of 2, you are having z. And minus 3yz is minus 30. Can you
Ma'am,
compare? Yes?
I mean, this one basically what I wanted to understand is that, so you have already put x as 1, right?
I did not take x as 1, no. I did
Oh,
not do that.
okay, you all differentiated it. Okay.
I am differentiating. I am differentiating this entire function with respect to x, considering this y and z as numbers.
So you put x as 0 over here, no ma'am, because 0 is in
No,
the...
no, no, no. I did not put x as 0 in the first step.
Okay,
No.
got it.
Oh, yes. Okay. You took everything, all of them as constants, and then you differentiated by x.
Yes.
Okay, ma'am. Understood, ma'am. Understood.
Okay, at last you put the value of y and z.
Yes.
Treated
So,
y and z as constants, ma'am. So they come out of the d by dx. Okay. ma'am.
yes, yes.
Understood.
Okay. Fine. Okay, now calculate these values dou f by dou x at 2, 2, 2. What is the answer?
-8.
Minus?
Minus
8.
8.
And what is dou f
8.
by dou z? This is also?
-8.
-8.
Okay, fine. So option 3 is correct. What about option 4?
-9.
-9. This is also correct. Okay. So I hope you all understood this particular exercise. It is just simply applying, first finding dou f by dou x and applying the values here. Okay. So just I will find what is dou f by dou z and dou f by dou y. Just this functions alone I will find for those who have difficulty. What is dou f by dou y?
Ma'am,
X
x
plus
plus
z
z plus
X plus
minus
Z
3x.
plus 3
Minus 3xz.
XZ.
Minus 3x.
Okay. Same way, what is dou f by dou z?
0 plus y plus
y,
x
x, x,
minus
minus
3xy.
y.
Okay, good. Okay, so the remaining part, whatever I have not calculated, please calculate and check. Okay.
So the upshot is whatever we are whatever is below that fraction, dou z, for example, in the last one, everything
Mhm.
else we should just put it as constant and just do normal differentiation.
Yes, yes. Okay. Fine. Okay, so another similar example here, maybe shall I just skip this because it is very similar to this one, or you want me to do this?
Just
Okay.
a cap.
Okay, let's do this. What is dou f by dou x?
3x square
3x square plus 3y.
Plus
Okay.
3y.
Okay, what is dou f by dou y?
3x.
0.
3x.
Simply 3x, right? So now what is, so the short form here is fx, fy. Okay, so what is the value of fx and fy for 0, 0? For 0, 0, the value is
same
0, 0.
0 only.
Yeah,
Here
both
also
0.
0.
0.
For 1, 1,
6.
6 and 3.
6 and 3.
And
so these two are equal, these two are not
Not
equal.
not equal.
And 1, 0,
3 and 3.
3 and 3.
3 and 3.
3.
3 on 3.
they are equal, right? So you see that dou f by dou x equal to dou f by dou y. Of course, this is not equal. So the first option is incorrect. Second option is correct. Third is incorrect. Fourth is correct. Fifth one, dou f by dou x is equal to dou f by dou y plus 3. Is that correct?
No, ma'am, it should
No.
be.
No.
False.
Okay, fine. So, okay. So now tell me what's going on here. What is dou f by dou x and dou f by dou y? What is the formula if you have a fraction? How do you find what is the u by v rule? Can you tell what is u by v rule?
v u
X
dash
square
minus u v dash divided by v square.
Yes. So you have u by v whole dash is equal to v u dash minus u v dash by v square. So you apply this formula and let's find the derivatives. What is dou f by dou x? Remember, y is constant. As long as you get used to this partial derivative, you write what is the constant so that you will remember it while finding the derivative. Okay, so you see that, so this is your v, this is your u. Okay, so you write your v as it is, x squared plus y, and in your u, derivative with respect to x. What is the derivative with respect to x?
y.
Y minus u and v dash. So x squared plus y with
2x.
respect to x is 2x divided by x squared plus y the whole square. So you have x square plus y square minus 2x square y, the whole divided by x square plus y square the whole square.
Ma'am, x square y plus y square, ma'am.
Square y square is
Where?
first
X
term.
square y plus y square. ma'am.
First term.
First term, ma'am.
X
X
square
square
plus
y
y v
Ma'am,
u dash.
I'm in the last part.
in the last
After
part.
equal to.
In the calculated part, x square y plus y square.
Ma'am, denominator.
First.
First term, first.
Here
No, right
No,
side.
calculated part.
After you multiply.
Denominator, it is not x square plus y square. It's just x square plus y in the
Yes.
result side.
oh yeah, okay, fine.
And ma'am, in the
I'm
numerator
also in the
x
numerator part.
square y
It should be x square
plus
y.
y.
Okay, thank you. Okay, fine. Okay, so now you see what is dou f by dou x. So same way you can calculate what is dou f by dou y. Maybe we can simplify this if you want. So how can we simplify this? This is y square minus x square by y, x square y, and here you have x squared plus y the whole square. Okay. So you need to compute it at the points 1 comma 1, 1 comma 0, and then 0 comma 0. At 0 comma 0, what happens? Is it defined?
No.
No, ma'am. The denominator becomes 0.
Ma'am, is
Yes.
this that the reason that if we substitute 0, 0, so the denominator and numerator becomes 0, so it's not defined?
Yes.
Okay.
Okay. So just a short break I will take. Meanwhile, you all calculate the dou f by dou y, and the remaining part we will discuss the answers within few minutes. Okay. Complete the remaining. We'll discuss it quickly. Okay, so have you all completed?
Yes, ma'am.
Okay, so for what is the value of dou f by dou y?
Y square minus x square y divided by x square plus y whole square.
The same.
Yes, ma'am.
No.
No, it's x cubed by x
Yes.
square plus y whole square.
Yeah.
Yes.
X cube.
X cube comes, ma'am.
Yeah. Okay. So now let's look at the options. You need to compute dou f by dou x at 0, 0, 1, 1, 1, 0. But before even checking that, at 0, 0, do we need to look at the partial derivatives or do we need to look at the question first?
Okay, so the function doesn't exist.
Yes, ma'am. We can directly look at the function only, because if it doesn't exist, it cannot have a derivative.
Exactly. So for the first option, directly from the function itself, we can say that they are not defined, right? Because the function itself is not defined at 0, 0, right? Yeah.
Yes,
So
Yes.
for the remaining options, we can look at the values. So fx, fy, what is the value of fx and fy at 1, 1?
0 and 1 by 4.
0 and
1 by 4.
so the option 2 is correct, right? Okay.
Yes.
So this is incorrect. What about 1, 0?
0 and 1.
Okay. So this is also correct. Okay. So is this problem clear for everyone? Yeah. Okay. Okay. So, okay. Now, what are piecewise functions in one variable? Do you remember? What are piecewise functions? For example, let us say,
ma'am, if they're not continuous, are they directly piecewise? Is that correct?
if they are not continuous, yes, more or less it's correct. So let's say f of x is equal to, let us say you have this kind of a definition. X when x is greater than 0, and let us say minus x for x less equal to 0. So how will the graph look like? So for x greater than 0, so remember for x greater than 0, it is just x.
Not function, ma'am.
So it is
V shape.
just this, right? But remember here it is a empty 0. And then for x less equal to 0, it is minus x. So minus x means which values will come? Here. Right? So it is this function actually.
Ma'am, in 0, it is defined because you put less than or equal to.
So when you are drawing the first part, it is an empty 0. And for
Yes,
the second
ma'am.
part, it becomes actually full.
Yes.
Okay. Okay. So now instead of this, suppose let us say I am fixing this variables now. So maybe I'm taking 1 and minus 1. Then how the graph will change?
Signum function.
So now you have for x greater than 0, the value is 1. And for x less equal to 0, it is minus 1. Okay. So these are some examples of piecewise functions. So piecewise function means for different pieces, the functions are defined differently. Okay. So for different pieces, the functions are defined differently. So these are piecewise functions. Okay. See, for some situations, we cannot say, like someone asked, can we say all discontinuous functions are piecewise? See, that is not exactly correct. To some extent, I said, right?
Yes, ma'am. I got one example. Suppose x minus 1 divided by x minus 1.
Mhm.
It is not continuous at 1, but it's just like a line. So I don't think it's piecewise. Yes, ma'am.
X minus 1 by x minus 1.
Yes, ma'am. It's basically y is equal to x. Except at 1, it is a 0.
Minus 1 by x minus 1 is y is equal to 1, right?
Sorry, ma'am. Y is equal to 1. Sorry, ma'am. Sorry. Y is equal to 1. Yes. So, but at 1, it's not defined.
Okay, so I guess, yeah, so whatever you are saying is kind of confusing. So let's not confuse the others. Let's stick to what is piecewise function for now. Okay, so for piecewise function in one variable, So here are some graph examples based on graph. So I first wrote the function and draw the graph, and straight away here are some examples of graphs. So here you see from 1 to the remaining values of x, the function is defined in this way. See, you see this function is also discontinuous, but for everywhere except this point the function is defined. So it does not mean that if you are just considering this part, it does not mean that the function is piecewise in this part. Okay, so whatever you said, it's not exactly correct. Okay, so let's stop that discussion at that point itself and continue with piecewise functions. So here you see that for this point 1, from the left hand side of 1 to the left hand side of 1, it is defined differently. To the right hand side of 1, it is defined differently. So to find the limit at 1, what do you do? How do you find the limit f of x as x goes to 1?
Left hand and right hand limit we have to equate, ma'am.
Yes. So what is the left hand limit of this function?
2, ma'am.
The left hand limit is 2. And what is the right hand limit?
3, ma'am.
See, the value of the function is approaching
3.
Okay, so you know that only when both of the limits are equal, the function is having limit at that point. So here you see that the limit does not exist at x is equal to 1. Right? Same way, look at this function. Now, is the function first of all, so here what is the value of f of 1?
2, ma'am.
2. Okay. Here what is the value of f of 3?
3, ma'am.
3. Right? And what is the left hand limit of
2.
f at 3?
2, ma'am.
Left hand limit is 3. It is 4, right?
Sorry, ma'am. 4, ma'am. 4. Yes, ma'am.
4. And the right hand limit is?
2, ma'am.
Okay. So this is the limit concept in case of one variable functions. Okay.
Ma'am,
Yes.
the value of f of 3 is 3 because there is a dark dot at 3. That's why.
Yes.
And ma'am, what's the limit? What is the value of f of 3 at 2?
This is the left limit. And this is the right limit. These are covered in math 1, I guess, right? Left limit,
Yes, ma'am.
right limit. Okay.
Ma'am, someone has raised their hand. I guess they wanted to address
Yes, please ask.
Could you explain this one 3 minus and 3 plus, please, once?
See, when you are approaching 3 from the left side of 3, where is the function ending?
4.
4. That's why the left hand limit is 4. Same way, when you are approaching 3 from the right side, where it is ending?
2.
2. That's why the right hand limit is 2. Clear? Okay, fine. So, in case of partial derivatives, what is that happening? Imagine you are having only for one point, either you can approach from the left or from the right. But if you are having a 3-dimensional space, how many directions from which you can approach one particular point?
The number of the dimension of the space, ma'am.
No.
Shouldn't it be infinite?
Yes, you can approach that point in several different ways, right? So just imagine, for example, the origin. How many ways you can approach the origin? In so many different ways, along x-axis, along y-axis, along z-axis, along the line y is equal to x, along the plane. So many different ways, along different curves, along y equal to x squared. Like there's so many different ways you can approach, right? Okay. So here is an example of a partial derivative. So whenever we are looking at partial derivative of a piecewise function. Now this is a piecewise function. This is one piece, this is another piece. Everyone listen carefully. If you are given a piecewise function and you are asked to do the partial derivative, and suppose one of the pieces just a single point, always use limit definition. So when is that you need to use limit definition? Everyone listen. You need to use the limit definition of partial derivative if you are given a piecewise function and one of the piece is a single point like this. Then for that particular point alone, you need to use limit definition to find the partial derivative. If you are straight away applying the partial derivative, you will you may end up in a wrong answer. So
Ma'am,
all this,
can we find the left hand derivative, right hand derivative, and compare the left hand derivative, right hand derivative, and at that point,
see,
I
no,
remember
no, no.
studying
The left
somewhere we can
derivative,
do that.
left and right, that concept is not there for multivariable calculus. Here we have
Okay.
something else. So during when we see continuity in the next lecture, let's discuss what we have to check. Okay,
Okay.
fine. So along any curve, we need to check. So that we will discuss in the next session. So first here, whenever you are having a piecewise function, how to find the partial derivatives. That is the part we are going to see. For the first part, it is the usual case. So for the usual case, how do you find the partial derivative for the first part? So let x comma y not equal to 0, 0. Now find what is fx. Everyone calculate dou f by dou x. How do you calculate? You using u by v formula. How will you calculate? Calculate and tell me what is dou f by dou x. So remember here y is a constant. So x squared plus y squared times of y minus xy times 2x divided by x squared plus y squared the whole square. So here x square y plus y cube minus 2x square y by x square plus y square the whole square, which is y cube minus x square y by x square plus y square the whole square. Is that correct? So note that this is for all non-zero points x comma y not equal to 0 comma 0. All non-zero points. Same way, calculate dou f by dou y and tell me.
Ma'am,
Remember?
in place of y, you keep x, and in place of
Okay, the function is a symmetric function. Yes.
yes,
So you see that dou f by dou y is x cube minus xy square by x square plus y square the whole square. Okay, fine. So we have found.
Yes, ma'am.
Sorry. Okay, so dou f and dou x, fx and fy we have found for non-zero points. Now let's do this with applying the limit definition. What is the limit definition? So to find dou f by dou x at the point 0 comma 0, so it is limit h goes to 0 f of, so remember you have f of a plus h e1
E1.
minus f of a. So you need to apply that here. So f of what is a? Your a is, so a plus he1 is,
Ma'am, how did you know to do with E1 and not E2?
because it is with respect to x.
So you're going to calculate dou f by dou x and dou f by dou y both.
Yes.
Okay.
Okay. So a plus he1 is 0 comma 0 plus h times of 1
0,
comma
1,
0.
0.
So
Sorry.
it is h comma 0. Okay. So you have f of h comma 0 minus f of 0 comma 0 divided by f h. So what is f of h comma 0? What is the numerator?
0, ma'am.
0. So 0 minus 0 by h. So already this is 0.
0.
So the answer is 0. Same way, what is dou f by dou y at 0, 0?
0.
0 only.
Ma'am, to find f of h comma 0, we just equated it to the original equation. That's it.
Yes, you
Yes.
simply have to substitute h here and 0 here. That's all.
Okay, ma'am.
Same way, here this is also limit h goes to 0, f of 0 comma h minus f of 0 comma 0. Because here you have f of a plus he2 minus f of it. Okay, and a plus he2 is 0 comma h. Okay, so divided by h, which is 0 again. Okay, so does the partial derivative at x and y of f and f with respect to x and y at 0, 0 exist?
Yes, ma'am.
And what is the value?
0, ma'am.
Both are 0. Okay. So the
Ma'am, suppose
yes,
one of them was 0 and the other one was 1. Can we say that the partial derivative exists?
yes, they are still existing. They don't have to be equal.
They don't have to. Okay.
Yes. So you see, if you just look at this equation and you are simply substituting 0, 0 and saying the limit does the derivatives do not exist, then it is going to be wrong. So always use the limit definition whenever you are having such functions. Is that clear?
Ma'am, a small query.
Mm.
Why did we find then partial derivatives, ma'am?
That is for the other part. We are finding partial derivative of f with respect to x and y. So we are finding it for the entire domain. So we found it for the first part and then we are doing it for the next part here.
Oh, no, like for checking partial derivative, if limit exists, we should not use, sorry, I could, is this a two-part question? One is finding partial derivatives and the other is checking limit?
No, we have done only finding partial derivatives. One is for the first part of the domain, the other is for the second part of the domain. That's all. So the second part of the domain, instead of just applying the formula directly, we are applying it the limit formula. Here we have used the derivative formula. Here we are using the limit formula.
Oh, okay, yeah, okay, understood, ma'am.
Okay.
Ma'am, we have done because we couldn't find it using the normal derivative for the second part.
See, it is not that we cannot, but this is the way we are usually doing to avoid certain mistakes. Sometimes it happens that if you are just applying the function, because see, it is just one particular point. So if it is just one particular point, just using this kind of formulas will lead to confusion. So we have to be careful and take the limits to exactly see what is going on. Limits will analyze what is going on around that point.
Ma'am, but in the second one, so basically, because if we apply this dou f by dou x, so anyways we'll get undefined, right? So that's why we are applying this limit formula, right?
See, it is not because it is undefined we are doing. Again, I'm saying it is not because it is undefined we are doing this. Whenever we are having functions defined like this and we are having a piecewise function where only one point is separately given like this, we are using limit function because we don't know exactly. See, in the case of one dimension, around this point, what is happening is very clearly visible. Okay. But in the case of multivariable function, it is not always very easy to visualize what is going on around this point.
Ma'am, suppose if it was not a piecewise function, then f of 0, 0 wouldn't exist at all. So if we put that in the limit form, then directly we would know that it's not,
Yes.
it does not exist.
Yes.
Correct, no, ma'am?
Yes, yes.
Ma'am, 1 second. Mayur, could you just please sorry, could you just mute your mic? Ma'am, could you just repeat, how are you checking the limit, ma'am? Like, if limit exists,
I am not checking the limit. I am using the limit formula for partial derivative.
okay, ma'am. You have calculated for 0, 0.
Yes.
Then how do you prove that it exists at 0? Like something should be.
See, because you see that if this value is undefined, then I will say the limit this derivative does not exist. That's all. If this limit does not exist, then the partial derivative does not exist. You understand?
Okay, it has nothing got with the non-zero part.
No.
It is asked only to check at 0, 0.
Yes.
So we'll only check for the 0, 0, and if it's luckily, sorry, not luckily, here we have got 0, so it exists and the value is 0.
Yes.
Okay, thank you, ma'am.
We are going too slow in this case. I'm not going to do these two exercises. Maybe in tomorrow's session you can do this two problems. These are quite simple
Ma'am,
problems.
tomorrow's session will be same 8 to 10 only, no, ma'am?
Same?
8 to 10 timing.
The usual TA session timings, yes.
Ma'am, there won't be an instructor session for all this?
This is an instructor session, right?
No, ma'am. Tomorrow it won't be an instructor session. It will be a TA session.
It is a TA session, yes. Okay. So I want to tell what is directional derivative today at least. Okay, what is directional derivative? See, just derivatives, as I told you, see, we are seeing first of all what is the derivative with respect to x, with respect to y. So in the while showing the graphs itself in the GeoGebra, do you remember first I showed what happens when y is equal to 0, y is fixed, and then I showed what is x, what if x is fixed, and then what is the other thing I showed? Do you remember, any one of you? What was the third thing I showed you? Does anyone remember? So it was along some direction. I actually showed y is equal to x, the line y is equal to x, and what was the graph? That was what I showed. Okay. So it means you can consider the rate of change along any given direction when you're considering the derivative of a multivariable function. Not necessarily fixing y or fixing x. You can in fact fix any particular direction and find it. Okay. So that particular direction, what is the unit vector you need to know to find the derivative? That's all. Okay. So for example, along the x-axis, what is the unit vector?
1 0
1 0. Along y-axis, what is the unit vector?
0 1.
Okay. So in that case, so along x your u is e1, right? And along y your u is e2, right? So can you see what is going on? So along x you usually have f of a plus he1, right? Along y you have f of a plus he2, right? So instead of u is equal to e1 and u is equal to, or u is equal to e2, if u is some other unit vector, okay, for example, if you are taking y is equal to x, then the unit vector along y is equal to x you are considering, right? So that particular thing you are adding up here. Okay, you are adding f of a plus hu. Okay, instead of e1 you are adding u, that's all. H times of u. Okay, so f of, here you are using x tilde, so x tilde plus hu minus f of x tilde. Okay, so instead of e1 or e2 I am using some other u, unit vector. This is the directional derivative. Directional derivative means in some particular direction. Okay, so whatever I said here, that is what is mentioned here. So if you are considering partial derivatives, they are special. See, this is a very important thing. What is the relation between partial derivatives and directional derivative? Partial derivatives are just the directional derivatives along the x-axis and y-axis. That's all. Okay, fine.
Ma'am, just one small confirmation. Whatever we're studying till now is all only for scalar multivariable
Yes,
functions, right?
yes.
Ma'am?
Scalar valued function is what mainly we are seeing. Only one topic in the, I guess in the next session we will look at vector valued. Otherwise, everything else is only for scalar valued.
Right. Ma'am.
Okay, fine. Okay. The rate of change of f of x comma y equal to x plus y at 0 comma 0 in the direction of y is equal to x. So what is the rate of change in this particular direction? Y is equal to x. How are we going to find? So if y is equal to x is the line you are considering, what is the unit vector
1
along
comma
y
1.
equal to x? Yes?
1 comma
1 by root 2 comma 1 by root 2.
Yes. Right? So unit vector along y is equal to x is 1 by root 2 comma 1 by root 2. Is that clear for everyone? How did we obtain this vector? Is it obvious to everyone?
divide with the norm, no, ma'am. Correct.
Yes. You take any vector from y is equal to x, the obvious vector is 1 comma 1. Divide by its norm, you get 1 by root 2 comma 1 by root 2. Okay? Fine. So you take any vector from the line and divide by its norm, you get it. Okay, fine. So now you see that you have the unit vector. So once you have the unit vector, what is that you need to do? So you need to use the formula. So duf at 0 comma 0 is limit h goes to 0 f of x tilde plus hu minus f of x tilde by h. So what is x tilde plus hu? X tilde, this is your x tilde. So what is x tilde plus hu then? Why so much silence? It's simply h by root 2, h by root 2, right? Because this part is 0, 0.
Yes, ma'am.
Yeah?
I just was drinking water, so couldn't.
Oh. So limit h goes to 0. So you have h by root 2, h by root 2 minus f of 0 comma 0. What is f of 0 comma 0?
0.
0. Whole divided by h. So I missed a f here. So this is limit h goes to 0. Now you just have to add them up. So you get 2h by root 2 here into 1 by h. The denominator h I am bringing up. So it becomes this. So what is your answer?
Root 2.
Root 2. Okay. So whatever we did for partial derivatives, the exact same thing. Only thing, instead of e1 or e2, now you are having u. That's all is the difference. Okay. So now can you do this same process for this function? So you are given this vector and you are saying that you need to find the rate of change in this direction. So what is your u?
4 by 5, 3 by 5,
Oh,
and 0.
yes, ma'am.
4 comma 3 comma 0 divided by its norm. So its norm is root 25. So 5. So 1 by 5 times of 4 comma 3 comma 0. Good. So you know what is your u. So what is the next step? So you need to find the directional derivative of f along u at the point. So at the point 1 comma 2
1,
comma
2, 3, ma'am.
Yeah. So if you apply the limit definition, limit h goes to 0, f of x tilde. So here x tilde is 1, 2, 3.
1
Right?
plus 4 by 5h, comma
Yes,
2
maybe I will
plus
try.
h, 3h
X
by
tilde
5
plus
and
h
3.
cube. Yeah. 1 comma 2 comma 3 plus h by 5, 4 comma 3 comma 0. So you have 1 plus 4h by 5, 2 plus 3h by 5, and then 3. This is a x tilde plus hu. What is your f of x tilde? Calculate and tell me.
Uh, 11, I guess, ma'am.
Yes, it's correct. It's 11. So you have limit h goes to 0, 1 plus 4h by 5, 2 plus 3h by 5 plus 2 plus 3 times of 2 plus 3h by 5 plus 3 times of 1 plus 4h by 5 minus 11. So if you simplify this, what is that you will get? Calculate and tell me.
Ma'am, here x tilde is just the unit vector, no? Just to confirm.
X tilde is this vector.
U is unit vector.
U is your unit vector.
Oh, sorry. Okay.
Ma'am, 32 by 5 I'm getting.
32 by 5. Yes, correct. It's correct. So when you simplify, you will get limit h goes to 0, h times of 32 by 5 plus 12h by 25 whole divided by h.
H, ma'am.
So you have 32 by 5 as answer. Okay. Is that fine? This problem? We simply applied the definition again. Is it clear? Yeah?
Yes, ma'am.
Okay. So for the next question, so the u is not given to you straightforward. So this is your x tilde. Now they are saying at 1 comma 0 in the direction 60 degree from x-axis.
Ma'am, here it's slope with tan 60, which is root 3. So it's
Cos 60, sin
y is
60.
equal to root 3 x, I'm assuming.
See, you are having your x-axis here.
Yes, ma'am.
Let's
Y is
take
equal to root 3x.
y is equal to root 3x. Why?
That is the line, ma'am.
Why it is root 3x?
Because tan 60, that's...
Okay, you are calculating the equation of the line. Y is
Yes,
equal to
ma'am.
root 3x. Yes, you
Yes.
can look at that. I guess this equation is the correct one. But if you are using the other way, that is, if you are taking 60 degrees from here, what is the polar coordinates formula? You already know. What is the where is
Cos
the
theta, sin theta.
Yes, cos 60, sin 60. So what is cos 60?
Half.
And what is sin 60?
Root 3 by 2.
Okay, so does it match with your y is equal to root 3x? So 1 comma root 3, and what is the norm of 1 comma root 3? It's 2, right?
2.
It's matching, I guess. Yeah.
Ma'am, a small confirmation about the polar coordinates.
Mm.
If they ask from y-axis, how should we? Could you do it for general form for four coordinates?
Okay,
Once could you
if
just
you
do?
are asked from y-axis, then you simply see already
90
90
minus
degrees
theta,
there. 90
is
plus
that
60 is going to
90?
come. Okay, so what is cos of 90 plus 60? Use trigonometries, that's all. Okay, fine.
Okay, ma'am.
All right, so here you see that now you have to find DUF at 1 comma 0. So what is that formula? I will just write you what is that you need to do. You complete the calculations. So you have your x tilde here, x tilde plus HU. So you have 1 plus h by 2 comma root 3 h by 2 minus f of 1 comma 0 by h. So complete this as a homework. Okay, so the final answer is root 3 by 4. Okay, so here you need to use chain rule and L'Hopital rule or L'Hospital rule, however you call it. Usually it is L'Hopital rule. So chain rule and L'Hopital rule has to be used. So they are hint I have given. So use these two for completing this computation. Okay. If you have doubts in this computation, you can discuss in tomorrow's session. Okay. Fine. So what are the properties of this directional derivative? Just like the partial derivatives or the usual derivative, linearity property is preserved. Product rule is there. The product rule is the usual product rule we have, right? What is the usual product rule? UV whole dash is equal to U dash V plus V dash U. The same formula applies here as well for directional derivative.
Ma'am,
Okay.
if it applies to directional derivative, then it'll directly apply to partial derivative.
Yes.
Okay.
Okay. So the same formula for quotient rule also. So u by v whole dash, whatever we have formula, vu dash minus uv dash by v square, the same formula is applicable here as well. Okay, fine. And then you have, yeah. So now we have some problems here. Find the directional derivatives of the following functions in the direction of the unit vector. So now can we do the same without using the limits? How can we do this without using limits?
Partial derivative.
Yes, how to use partial derivatives. We have not yet seen that. Okay, so there is one method which I am going to tell you now. So where I should have given space to explain that method here actually. Okay, so where shall I say, do I have space? Okay, here I have space. So directional derivatives using gradient. What is gradient? We are going to see now. Gradient is nothing. So what is this gradient?
Slope, no, ma'am. In 11th and 12th gradient.
Yes, but here for multivariable function, what is gradient? So the gradient is a function. So suppose you are having a function f from Rn to R. Okay, you are having f of x1, x2, xn. What is the gradient function? The notation is del f. Okay, it is simply dou f by dou x1 up to dou f by dou xn.
Ma'am,
See,
what
all
is
the
that
partial.
symbol?
Sorry,
Delta, opposite delta, ma'am. What is that symbol?
we call it just del, capital del.
Okay.
Okay, so you have dou f by dou x1 up to dou f by dou xn. Okay, and if you want it to be at specific point, you just have to find the partial derivatives at that point. That's all. Okay, so this is your gradient function. Now, how to define directional derivative using gradient? What is the formula? The formula is that, so du f at a tilde is given by del f a tilde dot u. What is this dot representing?
Inner product.
Yes, dot product.
Ma'am,
Okay,
I
so
just
this is the
missed.
formula we are going to use. Any questions?
Ma'am, I just missed one thing, and the part of lecture is directional derivative.
Sorry. Okay, fine. Okay, so the directional derivative part is here. So here you see now, if you are applying this formula, what is your gradient function? What is fx?
Partial derivative with respect to x.
What is the value of the
1.
Okay, what is fy?
1.
1, right? So now del f is fx comma fy. So the value of del f is 1 comma 1. Okay, so now du of f is del f dot u. So you will simply have 1 comma 1 dot u1 comma u2, which is u1 plus u2.
Ma'am, could you once repeat the gradient stuff? I couldn't, like, it was just a flash.
Okay, so gradient is simply this function which consists of the partial derivatives with respect to each variable written component wise. That's all. Okay, and the formula to compute the directional derivative using gradient is duf is del f dot u, dot product with u. Okay, so this is the formula. So for example, maybe we can try for one of these functions to visualize. So what is the del f for this function? What is fx for this function?
Y, only y.
Y plus
Y plus Z.
What is fy for this function?
Okay,
X plus Z.
Fz is
X plus Y.
X plus y.
y plus x or x plus y. Yeah. So now you know that del f is fx comma fy comma fz.
FC.
So it is y
Y
plus
plus z.
x
X
plus
plus
z.
z. Y plus x.
Now what is del f at, this is your x tilde, 1 comma 2 comma 3. What is that? 5 comma 4.
Directly substituting, right, ma'am?
Yes, yes. 5 comma 4 comma 3. Is that correct?
Yes.
So now your duf at x tilde is equal to del f at x tilde dot product with u. So 5 comma 4 comma 3 dot product with 1 by 5 times of 4 comma 3 comma 0. What is the answer? So you have 4 plus 12 by 5 plus 0. So which is 32 by 5.
Ma'am, could you just go back to the problem before this one, if you don't mind?
This one?
No, ma'am. I think x plus y.
This one?
Yeah, ma'am. This one. So, ma'am, in this one, so plus y.
Your
So in,
del f is a constant function here.
okay, okay,
Okay.
okay, ma'am.
So you see that in this case, both the values are matching. Okay. So either you use this formula or you use the gradient formula, you will end up with the same answer. So both the formulas are clear for everyone.
Yes, ma'am.
Okay. Fine. So now this is the problem we actually did exactly now, right? Xy plus yz plus zx, right? So this is done, right? So this is what exactly we did here. Xy plus yz plus zx, right? So this is your gradient function. So del f dot u is what you will get here. Okay, so this is done. Okay. What about this part? What is fx and what is fy here?
Ma'am, fx is cos
Y
Cos xy.
cos x.
y cos x.
Y cos xy.
Sorry, ma'am. Y cos x.
Chain rule you have to apply. Don't forget, you have to apply chain rule. And for
Right.
fy, it is
X cos
Ma'am,
X.
can't it be cos xy times y?
it's the
Is,
same.
oh yeah,
Multiplication
okay, yeah,
only.
yeah, okay, done.
So use chain rule. Okay. So we have found fx and fy. So duf at any point a tilde is given as del f at a tilde dot u, right? So you have y cos xy comma x cos xy dot product with u1 u2. So you have u1y cos xy plus u2x cos xy. So u1y plus u2x cos xy. Okay. So this is your
Ma'am,
formula.
in place of xy, can't we substitute inside cos xy
Yes,
u1 u2?
yes, yes. Where? Here u1, u2 won't come. Why? We see del f at,
Oh, okay, yeah, chain rule. Yeah, sorry.
so you will have actually u1 a2 plus u2 a1 cos a1 a2. This is what you are getting, right? So everything is at
Yes, ma'am.
a1 a2.
Ma'am, so
Yeah.
ma'am, what is this DUF A tilde exactly called, ma'am?
See, it is the rate of change in the direction of the unit vector u. It is called the directional derivative of f in the direction of u.
Sorry, ma'am, I missed.
Which unit vector again? Could you specify? I forgot.
Sorry, what?
With the two unit vectors, no, ma'am.
With what? Sorry, I don't.
Directional, ma'am. Could you just show that slide where you explained directional?
Directional derivative. See, I did not give any figure for this directional derivative. See, instead of e1, e2, here you are having some other direction u. That's all.
Oh, okay, ma'am. And the directional. So, with respect to what vector did you compute just now the directional derivative?
See, what is u? I have not taken. U is just u1, u2. I have considered. I have not.
Oh, okay, ma'am. Understood. Yes, yes. Here it can be. So we can put any unit vector and get the directional derivative with respect to. Okay.
Yes. Okay. Okay. So I guess I have only this and one more problem left. So no big deal. We have almost completed the main part of this session. See, what are the main things we have seen? So we have seen what are multivariable functions. So mainly we have scalar valued and vector valued multivariable functions. Then we have partial derivatives with respect to x, with respect to y. So one is the limit formula and another one is the direct formula. So direct means I'm saying that derivative formulas, right? And then we saw directional derivatives. One is using the limit formula, the other one is using gradient. So these are the things we have seen so far. So please go through everything, because definitely for the remaining weeks, this is the base. Okay, so please go through everything before the next session, and whatever problems we have not completed, we will be completing, you will be doing it in the tomorrow's session. All right.
Ma'am, would the deadline for GA9 be extended, ma'am?
What is the deadline, current deadline?
19th,
19th, ma'am.
day after tomorrow.
Hopefully it will be extended. I will talk to the team and extend.
Ma'am, why is this sort of thing coming in every term, ma'am? Like, isn't there a solution where we have, like, because still 1 to 4 it is very good and nice, peaceful learning is there. From 5 to 9, in 3 days we have to complete each week. The deadline is coming, and it's a lot of rushy, and
Yes,
a lot
ma'am.
of syllabus has to be digested, and it's used to us for, like, we're not getting that kick while learning. It's like learning for the